Okay, so let's continue our discussion of continuity. Here I'm asking you to discuss the continuity of this function at x equal 2. And if you look at the function, we have f of x equals a linear function 2x minus 1 if x is less than 2, and it's equal to this quadratic function here 1 minus x squared if x is greater than or equal to 2. Now, we're only concerned about what's happening at 2, so let's start testing our definition of continuity at x equal 2. First of all, number 1, is f of 2 defined? Well, it says if x is greater than or equal to 2, we get this function. So equal to 2, that tells me that I can get the y value if I plug it into the second function. So plug 2 into this function and I get y minus 4, which is negative 3. So that tells me that f of 2 is negative 3, so therefore f of 2 is defined. So that one's taken care of. Alright, now the next one I have to consider the function. I mean the limit, I'm sorry, not the function, but the limit. So now let's talk about the limit. Well, to the left of 2, we actually get this linear function. So as we get closer and closer and closer to 2 from the left, it would actually give us the same value as if we plugged in 2 to this function. Because the closer we got to 2, the closer this function would be to 2 times 2 minus 1, which is 3. So the limit as x approaches 2 from the left is actually 3. But if we approach 2 from the right, then we're going to get closer and closer to 2 from the right. Since we're going to be to the right of 2, we'll be approaching 2 on this function. And so as we get to 2 on this function, we're going to get closer and closer to 1 minus 2 squared, which is negative 3. So the limit from the right is negative 3. Well, since the limit from the left is 3 and the limit from the right is negative 3, then the limit does not exist. And if the limit does not exist as x approaches 2, then this function cannot be continuous at x equal 2. Okay, so this one says discuss the continuity of this function at x equal 5. Okay, well, here we're given that if x does not equal 5, we get this function, x squared minus 25 over x minus 5. And that's good because obviously you can't plug 5 into this function. So this function is only if x does not equal 5. Now if x does equal 5, then we get the value 6. Okay, so we do know that the function is defined at 5. It tells us right here that f of 5 is 6. So f of 5 is defined. But if we take the limit of this function as x approaches 5, well, the limit of this function as x approaches 5, remember when it approaches 5, it's not going to actually equal 5. So to find the limit of this function as x approaches 5, I can use the replacement theorem, and if you factor the numerator here, you'll get x minus 5 times x plus 5, and then you can cancel x minus 5s, and you're left with just x plus 5. So using the replacement theorem, I can replace that function with x plus 5, and then take the limit as x approaches 5, and that gives me 10. So the first two conditions are satisfied. The function is defined at x equal 5. The limit does exist as x approaches 5. But now the next question, are they equal? Well, f of 5 is 6. The limit as x approaches 5 is 10. So since the two are not equal, these two values are not equal, so we do not have continuity on that one. Now, what would we have needed to put here so that we would be continuous as x approaches, or at x equal 5? What number could we put here? Is there a number we could put here? Well, yes, there is, because we know that the limit is 10. So the limit of the function is 10. So if I had changed this value to 10, if I change this to 10, well then f of 5 would be 10. So then the limit would be 10 and f of 5 would be 10. So if I simply change that number to 10 so that it matches the limit value, then f of 5 would equal the same value as the limit did, and it would actually do what we call remove the discontinuity. So with some functions you can remove the discontinuity and others you can't. Okay, discontinuity, as I just said, comes in two forms, removable and non-removable. A discontinuity at C is called removable when f can be made continuous by appropriately redefining f of C. So let's take a look down here. If we make this number here the appropriate value, we actually can force this function, this piecewise function, to be continuous at 3. Now notice up here, this portion of the function is not defined at 3, but that's okay because we only use that portion if x does not equal 3. So what do we use if x equals 3? Well, we're going to use some number. So to find out what number we need, what we're going to do is we're going to take the limit of this function as x approaches 3. And so the limit of this function as x approaches 3, if I use the replacement theorem, factor the numerator and cancel, I get that's the same as the limit of x plus 3 as x approaches 3, and that's 6. So if I make this number 6, which I did down here, if I make that number 6, then when you evaluate the function at 3 you get 6, and when you take the limit of the function as x approaches 3 you get 6. So therefore the functional value and the limit are equal, therefore this function is now continuous at x equals 3. Okay, now you can't always remove the discontinuity. You generally, when you're given a function like this, you can remove a whole, but you can't remove like the vertical asymptote. Okay, so if you look at this, remember you see here how you have a common factor of x minus 2 here and x minus 2 here. Well, that tells me we get a whole at x equal 2. So we could actually remove the whole at x equal 2, and I'll show you how we can do that in just a minute. But x equal 2 would be removable. Also, I have x here and x here. So what would make those 0? Just 0, right? So we could remove the discontinuity at 0. Now the only other number that I have on the denominator that is not common to the numerator, the only other factor, is x minus 1. So if I have x minus 1, then that means that if x equal 1, the denominator is going to be 0. But I do not have that same common factor up here, so that would be not removable. So x equal 1 would be a non-removable. Okay? And the reason is because of the limits. If you took the limit of this function as x approaches, let's say 0, and you took the limit of this function as x approaches 2, you actually do get values. Let me show you that. So let's talk about 0. We know that as long as x doesn't equal 0 and x doesn't equal 2, then we can cancel those and we just get x plus 5 over x minus 1. So let's replace this function with x plus 5 over x minus 1 and take the limit. So the limit as x approaches 0, if I plug 0 in, I get 5 over negative 1. So that's negative 5. So what that tells me is if I were to redefine this function to equal negative 5 when x is 0, it would actually make the function continuous at x equals 0. Now what about at x equal 2? Well, I can do the same thing. I can take the limit of this function at x equal 2, and when I take the limit of that, I get 7 over 1, which is 7. So if I redefine this function, the same function, to be 7 when x equals 2, then it would be continuous at 7. And the reason being is because by basically, you're basically letting, the limit equals negative 5 as x approaches 0. So if you define the function to be negative 5 when x equals 0, then you're making the limit and the functional value equal. Same thing with 7. You know the limit as x approaches 2 is 7. So if you make the functional value when x equal to 7, then you've pretty much made the limit and the functional value equal. So at holes you can generally remove the discontinuity, but you can't remove it at vertical asymptotes. If you go ahead and read this one, freeze the video and read it and see what I did here, and you'll notice that for this one I get a hole at x equal 2, so I can determine what the limit of this function is at x equal 2 and determine that I could remove the discontinuity if I wanted to. Now I just want to briefly talk about limit on a closed interval. If you had a function that was on a closed interval, say from this point from A to B, well, you couldn't use the same definition that you would on a function that say goes over the entire x-axis, has domain all real numbers. The reason is you couldn't talk about the limit of this function as you approach A from the left, and you couldn't talk about the limit as you approach B from the right, because the function is not defined outside of that closed interval. So what you have to do, you have to trade the definition with one-sided limits. Like I can talk about the limit of this function as x approaches A from the right, so that's what this is saying. And then I can talk about the limit of this function as x approaches B from the left. So basically you have to kind of change the definition just a little bit. You still want the same thing. You still want the limit and the functional values to be equal at those endpoints, but you can't say that the entire limit exists as x approaches A, because it's not defined on this side of A. And same thing for B, it's not defined on this side. So what you have to do is you have to kind of edit the definition a little bit. Okay, so just a real quick example. If we said y equals square root of 4 minus x squared over negative 2 to 2, is that function continuous on negative 2 to 2? Well, if you graphed it, it would actually look like this. It's a semicircle, and this would be negative 2, this would be 2, and actually both of these would actually have y values of 0. So f of negative 2 is 0. Well, also if you get the limit of this function as x approaches negative 2 from this side, then you'll see the function goes to 0. And if you get the limit as x approaches 2 from this side, you'll see that this function goes to 0. So for negative 2, the right-hand limit is the same as the functional value, and for positive 2, the left-hand limit is the same as the functional value. Now the last thing I just want to mention on the greatest integer function, the greatest integer function is not, the greatest integer function is actually a function that's continuous at all values except the integers. If you observe the graph of this, you can see it. Notice how there's no break in the graph here until you get right here. Then you have to jump. So at negative 1, that function's not continuous. Then there's no break here. So at 0, you have to jump. So the function's not continuous. And then you get to 1, and you have to jump. So the function's not continuous at 1. So basically, the greatest integer function is a function that is not continuous at integer values. And that pretty much completes the lecture on continuity.